When you begin a data science project, say in Jupyter Notebook or R or MATLAB, irrespective of what platform you choose to, perform machine learning, you always begin with exploratory data analysis. Correct? And in fact, this is where the bulk of your time is spent exploring the data. Which features are relevant? Which features are uh, need to be cleaned? Right? You choose your label if the label even exists. And once you have explored the data and you understand the different characteristics of your data, and then you proceed to perform feature engineering, right? You reduce your features, you discard irrelevant data, you interpolate missing data, for example, you decide what is numerical, what is categorical, and then once your features are ready, you have this subset of the original data, which you can then pass onto your machine learning model. After the machine learning model has completed and you have produced predictions, you've classified data, or you've done regression, you then want to represent data. What does that mean? Either you're going to turn these data into an analytics dashboard, or if, say, you're a social media company, you're going to be streaming this data out to people. If you're Netflix, for example, you'll be streaming out graphs. Data can be represented in different shapes. It can be in the form of, it can be tabular data like a matrix, or it could be trees or graphs. So we're not concerned with how the insights of data or let's say the problem outline of the data, but how we deal with data, from exploratory data analysis all the way to streaming out data or representing data. So let's see what mathematical techniques are used in machine learning specifically, and why you'd want to explore them further. Right? We have, when you collect data, whether it's in the form of CSV or TSV, or use SQL to query data, you have lots and lots of columns. Okay, let's assume we're talking about tabular data. Okay, imagine an Excel sheet. But before you begin machine learning, you must choose the right features. Right? This is what we call feature engineering. You choose the correct features. One problem is that even though you've cleaned your data, and you're left with the columns that are relevant, some of those features, some of those columns may be redundant, unnecessary. And it helps to reduce the dimensionality of your data. Let's say, for example, we're looking at a data set that has to do with people, and their heights and weights are strongly correlated. Leaving height and weight in that data set doesn't necessarily help the model learn important parameters. Instead, it increases the dimensionality of the data, which makes it harder for the model to learn. So one thing that we could do is perhaps collapse the data, reduce the amount of the number of features that are in your data set. How do we do that? One of those mathematical techniques with which this is accomplished is principal component analysis, PCA for short. This is a technique from linear algebra. Now, in order for you to understand how PCA works, you must understand the nature of matrices. Matrices are very special mathematical objects, and they take advantage of this diagonalization of elements. This picture you're seeing here, this figure, is what we call support vector machine, represented here by this yellow rectangle. Imagine that this is a three-dimensional coordinate system, and these circles are your observations. Okay. Now, PC is one way to reduce the dimensions of your data. This one is using support vector machines. It's not listed here, but here's how it works. You find a hyperplane, and you try to slice your data in such a way where your observations are divided into two. Classification. Classification with classifying multi-dimensional data is rather challenging to do. This is where supported vector machines come. And in order for you to understand how supported vector machines work, you need to go back to how matrices are constructed. And matrices, again, use this idea of diagonalization. Here's another reason why you want to consider linear algebra. This is what we call a covariance matrix. Again, the covariance matrix uses the diagonal of the matrices, the diagonal of this matrix, to represent the variance of a data set. The variance, of course, is how you measure the dispersion of your data. Except variance does not have it does not have a closed interval. It can go from negative infinity to positive infinity. So when you want to know the covariance of two features in your data, you need to have a reference point. You need to know what is a high variance, what is a low variance. So what you can do is you measure the covariances of all your features in the lower triangle and the upper triangle, and then you can compare the covariance against the variance which is aligned on this diagonal to see. So you have a reference point, so you can see, are they high? Is their covariance great or is it low? And of course, covariance is what you use to calculate correlation. So again, this is why linear algebra is so important. There are two parts to linear algebra. One of them is matrices, and of course, systems of linear equations. Let's move on to optimizing your model. Optimization itself is a mathematical subject. Optimization includes differential calculus, differential and integral calculus, and of course, linear programming. Linear programming is, let's say, a subtopic, or it's a branch of mathematics. It's a branch of mathematics inspired from probability theory. A lot of the notation in linear programming comes from both linear algebra and probability theory. So what are some techniques for optimizing your model? Well, what does optimization mean? Let's say you've trained your machine learning model and you want to see you want to make the model more accurate or reduce the loss of the model. Well, some of you may have heard of gradient descent, right? Which is, if you look at this picture over here, this is your weight space. This is your weight space. And if you want to find the weight combinations that will give you the lowest possible loss, that you're optimizing your model, in other words, you need to perform a technique called gradient descent. Gradient descent uses partial differentiation. Again, this is calculus. Then there's another topic called linear programming. Linear programming is about finding, well, let me rephrase that. Linear programming involves these components we call constraints, which are represented by equations. So these constraints, let me give you an analogy. Let's say you're trying to find the optimal route for a logistics company. You want to find the optimal route that will maintain their level of revenue while minimizing their costs. This involves a system of equations. System of equations is what we learn to deal with in linear algebra. So to optimize your model, not only do you need to know differential calculus, integral calculus, linear algebra, and probability theory. Then there's a technique in machine learning called grid search, which lays all the parameters of the model, and you will use this brute force kind of technique to find the parameters that are optimal for your model. That is done with graphs. Again, graph comes from graph theory. So just there, I've listed 5 mathematical disciplines that you would need to be familiar with in order to optimize your models. If you want to go beyond the code, if you want to go beyond programming in Python and TensorFlow and Keras and scikit-learn and go under the hood, so to speak, to understand what those, programming methods are doing, what those libraries are for. These are the mathematical topics you have to care about. Again, I only have 10 more minutes left, so I'm trying to give you as much information as possible. Estimation of probabilities. Again, machine learning is also known as that is what it used to be called. It used to be called statistical learning. So if you have a model that is going to classify data, say for example, let's say for example you want to classify, you want to tell oranges and apples apart. There is no decisive answer. Every observation is going to have associated with it a probability, which of course is a number that goes from 0 to 1. This probability number is very central to probability theory. Now, there's a topic called, for example, if we want to know the cumulative probability. So let me take a step back. In probability theory, we have a set of functions for probability functions. There is probability density function, probability mass function, cumulative mass function. These different functions allow you to measure the combined probability of multiple observations. If you look at this picture here, this is the bell curve. To generate this bell curve, we have the normal distribution, okay, also known as the Gaussian distribution. Now, if you want to measure the cumulative probability under this bell curve, you would need integration from calculus. So if you have a model like Gaussian distribution, the Gaussian mixture model, I should say. The Gaussian mixture model, in order to understand how the Gaussian mixture model works, you would need to understand probability theory, but then once you deal with continuous quantities in probability theory, you must then bring in calculus. Because when you if you were to open a textbook on probability theory, you would find a lot of references to integral calculus. So even though the textbook is called probability theory, it assumes you have a background in integral calculus. Okay? Then of course there's a type of machine learning we call reinforceable learning. Everything in reinforceable learning is from probability theory. So probability theory, integral calculus, differential calculus, and Markov processes, a subcategory, a branch of mathematics also inspired from probability theory. So that's 4 or 5 mathematical subjects in order to understand how probabilities are measured in machine learning. Then representation of data. So in computer science, we have 2 types of data: linear data structures, non-linear data structures. Linear data structures, everyone would know. These are arrays. In Python, they're called lists. If you're a mathematician, they're called vectors. You have this object, this mathematical object, in which you have elements, and each element has associated with it an index. Everything is numbered from 0 to n. These data structures are very simple, but they don't work for many. They're not ideal in many situations, especially in social networks. Something Dr. Federico is going to talk to us very soon. Now, there are 2 main types of nonlinear data structures: graphs and trees. 2 different data structures used that are the primary data structure in social media applications like Facebook and Twitter and YouTube. Now, to understand nonlinear data structures, or both of these data structures, you have to look into discrete mathematics. In particular, set theory, graph theory, and yes, for nonlinear data structures, just graph theory. Just the basic concept of edges and vertices will do. So This is especially important if you're going to be working with big data. In fact, uh, machine learning is not really useful unless it is used to deal with large volumes of data, big data, in other words. And in big data, we use libraries like Apache Spark. In fact, that is the predominant library for big data, Spark, and Spark uses graphs. Graph data structures are the heart of this technology. Okay, and again, to understand that, you have to cover discrete mathematics. So if I want to wrap this up, okay, here is a list of mathematical concepts with which you must be familiar to become, well, not to become, but to really understand machine learning in depth. So even though at the heart of machine learning is statistics and probability theory, there's a lot of mathematical topics that surround machine learning. But if I were to list them, if I could create a short list, it would be this. First and foremost, functions, because as a data scientist, you are modeling data, and functions are very important in modeling. You need to know different types of functions, polynomial functions, trigonometric functions, basically linear and nonlinear functions. You need to understand how to approximate functions, how to find unknown functions. That is what differential equations are about. You need to understand different shapes of functions. That is what you learn in algebra, that polynomial and trigonometric functions. You need to know how to approximate functions. There's something called numerical methods. Matrices and vectors, that goes without saying. So if we work with neural networks, so neural networks are matrices are at the heart of neural networks. Linear algebra, we already talked about. Sets and sequences. I mean, sets and sequences. The notations of sets and sequences are pervasive in all mathematics, irrespective of what types of mathematics you're looking at. Sets and sequences are used a lot, so you need to know the notation. Calculus, I already touched on that. You need to know the three types of probability functions if you want to understand different type. If you want to understand the shapes of your data, if you want to understand probability distributions, you need to know those three types of probability functions to which I referred. Combinatorics, that's central to probability theory. Finite state machines. Now, if you're someone who's interested in natural language processing, you may have heard of regular expressions. If you want to understand regular expressions, the best way to learn that is to start with finite state machines. Discrete mathematics. Let me just say this. Discrete mathematics will, if you find a textbook on discrete mathematics, you will learn about item number 1, item number 4, 6, 7, 8, and if you're lucky, number 9. 6 out of the 9 topics that I've listed it here, you can cover in discrete mathematics, a mathematical topic that assumes no prerequisites. If I can rephrase, if you're someone who's new to data science and you want to get into the mathematics, you want to understand the mathematics thoroughly, the best place to start is with discrete mathematics.